So my name is Claire Rosemary, and my thesis title is Bio-inspired Nanophotonic Devices to Control Light Emission on a Chip. So my project basically involves taking designs from nature and natural systems, and they've already undergone billions of years of evolution to optimize their light interactions. This is like flowers, leaves, butterflies, that kind of thing. And I apply these designs to nanoscale devices. So to get a rough idea of scale, if I took the designs that I'm working on and put them in a row side by side, I could get 10,000 of these in a 1 centimeter long line. So I'm primarily looking at golden angle Vogel spirals, which is the pattern that you can see in sunflower heads, or the small black display in the image on the bottom right. So on the left is an image that I've taken showing how light is emitted from this design when it's excited by a laser. The equations that you can see is how you make these spirals in polar coordinates. The conversion between the X and Y with polar coordinates is what you can see in the graph. So in this equation, A0 is a scaling factor, N is the value for the number of holes that you want in your structure, and alpha is basically the golden angle. This is how you take a Vogel spiral and turn it into a golden angle Vogel spiral. Now, this golden angle you can find by taking 360 degrees and divide it by the golden ratio squared. And this is particularly interesting because, as you may be aware, the golden angle is found all throughout nature as well. Now, these designs are really pretty in theory and in practice. However, why are they also incredibly useful? Why is better light emission from chips a really useful thing in technology? So these devices allow for quantum light emission, which is an emission where a single photon, or a single particle of light, is emitted in a steady stream from the surface of my samples. So this quantum emission can be useful for quantum communications, which is an incredibly secure and encrypted method of communicating with people. It's literally unbreakable unless you intercept both the code and the key. However, if you start intercepting one or the other, the people sending and receiving can see that you've started intercepting this code, and they'll just stop the transmission. So the message that you were trying to break, just it will stop. So these devices, the golden angle Vogel spirals, are also particularly exciting because it's been seen that you can encrypt orbital angular momentum into these photons. Now, this is a type of spin, and it provides an extra degree of freedom in the emission. Now, this is also an extra dimension in space in which you can encode information. So this can be seen in the diagram on the upper right, where L is a quantum number. I chose a quantum number of 1 as it's the most simple to visualize. The photon of light is not actually spinning, which is where it gets quite confusing. However, the best way to visualize it mathematically is to look at a packet of light and see that the direction in which it's propagating is rotating around the axis in which the direction it's going in. This is really useful for applications like quantum communications again, because it means you've got an extra degree in which you can encode your information, so it's even harder to break. But it also means you can apply it to things like multidimensional data storage. So whilst the entire world of technology is expanding rapidly around us, we need ways of storing information. Now, this adds an entirely new dimension. So you can have 3 dimensions of storage, whereas currently we only have 2. So with this, I plan to further enhance light matter interactions of my devices so I can get even more single photons, which makes quantum communications even more reliable. But also I'm hoping to advance technology.
Sorry, I'm going to have to stop you there. Okay, sorry, just went over a little bit.